All right, so I have this problem kind of color-coded here. So again, it's the 3 pieces of information. You've got the purple, the green, and the blue over there. So right now, we have initial information, and this is the initial, it needs to tell you what it is. That's the initial concentration of H2, and this is the initial concentration of I2. At equilibrium, we have this value. And we don't have anything for Kc, so most likely they're going to ask you, can you solve for Kc? Or they're going to have you solve for everything at equilibrium since we just have one, which is really easy to do. So it's one of those kinds of situations. You can start to see where these problems are going when you understand the problems. There's one more piece of information they don't ever have to give you about initial, and that's because you also always know that any product is 0. So let's fill this in really quick. We've got 0.348, we have 0.567, and we have that being 0. And I can go ahead, this section here, I can fill in because it's just the first column added together, which has a negative x, so it's really subtracting. But 348 minus x, 0.567 minus x, and then we have 2x. At this point, it tells us we know what I2 is at equilibrium. So it's saying that we actually know that this is really 0.416. So that means that we know x. 2x equals 0.416. What is x? We'll just divide both sides by 2, and you get 0.416 divided by 2. X is equal to 0.208. As soon as you know that x is equal to 0.208, then you also can plug x in over here, and you can find out what these two are at equilibrium, because you know x. So it's just the 0.567 minus 0.208. So that gives me 0.359. So that's this one at equilibrium. We know that one at equilibrium. And then the 0.348 minus my x, 0.208, is, 0.348 minus 0.208. And then that's just 0.140. Now, if they just want to know things at equilibrium, there you go. You got them. If it then wanted you to solve for Kc, well, you have all the numbers you need to solve for Kc. You would just plug in 0.416 squared times the h, which is the 0.140, times the 0.359. So do you kind of see how just having this information will let you get to this or the equilibrium information? So you just need a few types of information. So let's change it up. What if instead we didn't know this term, but we knew that this one was 50.2? And I just made that up. It's not really the real value for it. So let's say that we know that. So I don't know any of these values, and I don't know, I do know all my initial concentrations. I didn't change that. What I changed was knowing what this one was. So how do you get to the equilibrium value if that's the case? Well, you just, I'm trying to color code it again. Well, since I know what Kc is, this 50.2, I don't know why that popped up. I need it to stop. I'm just trying to write here. Okay, 50.2. Since I know what K is, I can plug this in, this in, and this in, and I can figure out what the equilibrium values are, because that's what's having me solve for. So I can plug in 2x squared. I can plug in 0.348 minus x and 0.567 minus x. And I've got a way to solve this that's easier than having to use your graphing calculator. But you can imagine you can just plug all this in, and at some point you'll get what x is equal to. Once you know x, you know that 2x is hi. You know that number minus x is that one at equilibrium, and that number minus the x, let's say x is 1 or something, then you know that that's 2. I guess it would have to be 0.1. Then you know that's 0.2. You know that that's 0.467, and that's 0.248. So do you kind of see, like, I had 2 pieces of information, and I could solve the problem in a way so that I could get to my equilibrium values. You can also work the problem. Let's say we did have those equilibrium values, 0.418. Let's say that was the equilibrium value. And then let's say that we know the Kc, but we don't know these. We still know zero product, right? We still know that. But let's say that we don't know those two terms. Most of the time you are given one of the two, or it'll say that, and I'm going to do it this way, the concentration of reactants are the same. So we would put something else in, like maybe a question mark or something like that. You know, like I don't know what that is, but I do know what X is. So like question mark minus X, question mark minus X. I know that's a funny way to do it, but I do know what X is. So this is 0.418. If 2X is equal to 0.418, then I just divide both sides by 2, and I get that X is 0.418 divided by 2, 0.209. Then I can also plug this in as question mark minus 0.209, question mark minus 0.209. We could call that an I for initial also, and we know that term. So now, since we know what K is equal to, we can plug in those values, 2X squared, and then we have the 1. I'm going to call it question mark, but if you want to call it initial, that's fine. 0.209, and then, minus 0.209. And sorry, I didn't mean to put a 2x in there. I meant to put in 0.209 equals 50.2. So now again, I just have one variable, the question mark, or whatever letter you chose to use it for. So I can solve for those terms. So I know that's kind of a lot all at once. So what I'm just trying to emphasize until you get a chance to practice some of these problems is there's kind of like areas of the chart where you definitely somewhere in the problem are going to have this information, either the purple and the green, you need the blue, or you'll have the blue and the purple and you need the green, or you see what I'm saying? Go have those regions that you need to know.